I don't know. Alright, so I see that you've drawn what are these things that you've drawn called?
The equipotential lines,
Yeah, so do you know what those represent?
where the charges equal at all points. Around
Does anyone have a different way of saying that?
the voltage is equal.
Right, so what does that kind of mean?
It's the same distance.
Same distance from what?
Central distribution of the charge.
So, well, you're on the right track, but think of it this way. If I kept a charge at this point, how much force would it feel in whichever direction it's attracted to? Like, versus if I kept it at this point, like, would there be a difference or would they be the same?
It'd be different.
It will be different, right? At one point it experiences more force, and another point there's another, right? So what if I took that charge and kept it at this point, or this point, or this point? Would that be different, or would that be the same?
That'd be the same.
That would be the same, right? So really, the equipotential field is the points at which the charge experiences the same amount of force relative to another point, kind of thing. So at the circle you've drawn, the charge would experience the same amount of force at every point, versus over here, the charge would experience the same amount of force at every point there. So that's what the equipotential lines are about. So do you know what the field lines would look like then?
They should go out, but I don't know
You don't know why?
why that happens because of. I don't know how to explain why that happens because of these.
Does anyone have a guess?
Oh,
Maybe because there's like a decrease in.
So actually the field lines point in the direction, so it's not necessarily like talking about the magnitude. There's something else that talks about the magnitude of field lines, but I'll talk about that after we figure out what. So field lines are just telling you the direction in which, like if I put a charge here, which direction it would move in. So you're right, you know that it goes out like that.
yeah. And
But-
this is positive, so that's why it goes out.
Right, that's the intuition behind it. But say if I didn't have a point, but I had like a bar of like instead of this being a point, I had a bar, something like this. Would the thing still look like that? But you can't really draw it because it's like not a point, so you can't really draw a circle from like a line, kind of like, you know, you need a center for a circle, right?
Yeah.
So do you have a guess of what like relationship there is between the field lines and the equipotential lines?
Just like less force.
So that's I like how you're thinking, because you're right that it does change as you move further from the point where it's experiencing the thing from, the attraction or repulsion from. But we're trying to figure out like what the direction always looks like. So if you like do all these experiments, really like do it on this one and do it on this one, and you try to draw the field lines, you'll actually discover that they all happen to be perpendicular to the equipotential thing at that point.
I forgot about that. Okay.
Right.
Yeah.
But see, it's not something that you gotta just like remember, like, you know, like it's perpendicular. If you actually do these, you'll see that's how it is, and start making intuitive sense to you. Because what you said earlier was right, that it's going. Oh, it has to go away from this, right? Because this is the point where.
Because if it's perpendicular, it couldn't also be perpendicular this way. So how do you know that they go out?
So that depends. So like we always in physics, it's always assumed that we take a test positive charge. So if you put a positive charge here and this is negative, it would go towards this. Versus if it were positive, it would go that way. So you can just do an experiment. You can
You just know because this is
clip this.
positive.
Yeah, you just clip this here and clip this here and see like what kind of readings you get, and that should probably tell you something.
Yeah, then it would go.
I would actually recommend you try that, because I might be wrong, because I think when we did that.
No, it's.
Oh, it is? Okay, never mind. So, but even then, you shouldn't believe me. You should always convince yourself. So, that's what it is. Any other questions?
I think that's good. Thank you.
No problem. Thank you so much.
Okay, so we just. It's perpendicular.
Hey, so we're just like verifying your answer on this. So it says explains how you're able to determine the field lines, and we're just saying that like they're perpendicular and they're all
Perpendicular what?
to the equipotential.
Lines, right?
Yeah, and then they're all of equal magnitude per line, but then also like the further away it is from the
Wait,
point
they're
charge.
of equal magnitude per line?
Yes.
Along the equipotentials, they're of
So, I think you're getting some concepts confused here. Stop that. Okay. So actually, electric field lines just show the direction. Their like length don't really mean anything per se.
Right? Aren't they just coming from the point charge out?
Yeah, you can draw the line as long as you want. Like, but you're basically trying to show that it goes that way.
But then, how would you say you're able to determine it from the equipotential lines?
So, if you're trying to find something perpendicular, you need another line to find it perpendicular too, right? You can't just have like, oh, draw that thing perpendicular, but you need perpendicular to what? So that's basically why you need the field lines. Sorry, not field lines, the equipotential lines. So you draw field lines perpendicular to the equipotential lines.
Yeah, but the direction. How would you determine direction just from the equipotential lines?
So, say I have this equipotential line, which is a circle. So, if I have a charge at this point, I want to know where the charge is gonna go. I'll just like assume there's like a tiny line here and draw a line perpendicular to it.
Okay.
And that's how I know that's the direction where the charge goes.
Yeah, but you know, like some arrows are pointing in and some are pointing out.
Okay, so say I kept a positive charge here. How do I know if it's going in towards this or out? Do you want to answer that?
Wait, the positive?
If I kept a random positive charge here,
Well, it goes away from positive.
right, so it would really depend on what this is. So if you connect the red versus the black to the center, that's what depends which direction your lines would go in.
Oh,
You
so
get-
outwards.
Yeah. Oh, it depends outwards or inwards because
Well, like ours are going outwards with the red in the center.
right. So it really depends on like in physics, the convention is always to assume a positive charge is what you're like seeing the direction it goes in. So based on that, you decide if it's inwards or outwards. Do you understand that? You get it?
Thank
Okay.
you.
No problem. But since you brought it up, how would you know how strong the electric field is at a certain point? Because your lines aren't, you don't see that, oh, this line is that long, so it's that strong. That's not how they're represented. Do you have any idea how they actually do it? Yeah, that's something you can't really just like figure out, but I was just wondering.
I just know, isn't it like the equation, like some constant times charge over radius squared or something like that?
Some constant times. Well, that's the some constant times charge over radius squared. Okay, that's an equation for like it's almost the equation for electric potential. No, yeah, it is potential, right? That's a equation for potential. But I'm asking, how would you know the strength of field lines just by looking at a diagram? So
Oh,
physicists.
the amount of lines you draw.
Right, exactly. That's what it is. So physicists do this thing where if they want to know there are a lot of strong field there, they'll just draw a lot of lines. So wait, do you have a paper I can draw on?
Yes, I guess.
I don't want to draw on that. I guess I would draw on the whiteboard, but I don't think there are markers there. Okay, thank you. So basically, if you have like a magnet, this is not a really good demonstration because you're learning about electricity. This is the South Pole and the North Pole. You always draw like the magnetic field lines like this, right? So if you notice, like near this part, there's like a very big density of lines, but outwards they kind of get further and further apart, just because of the shape of the magnet. That's kind of how. That's why when we have a magnet, you always try to touch the end to something versus like the middle, because it's always strongest at the end, and that's mainly because like all the field lines are really like the geometry works out that way that all the field lines will be really close to each other at the end. So depending on what shape you have, the density of field lines you can tell just by the types of lines you can draw from the field line. So in this case, like because it's a point, like all the field lines just point outwards. So where do you think the field would be strongest? At the where? No, sorry. In this figure that you're.
What was the question?
So in this figure, like you have this point charge, you drew all the equipotential surfaces, but where would the field be the strongest?
Closer to it.
Right, because if you draw the field lines like that, so over here, these two lines are so far from each other, but over here, they're like pretty close to each other, right? So if you measure the distance between each line, that's one way you can find out the density of those lines. And that's how you can tell where the field is strongest or not. So if you ever like, if you get on a test where like you're supposed to tell where is field strongest, just draw the field lines and see like where the density of the field lines are. That might be the hardest way to do it, but if you really can't figure any way out, that's probably like your safest bet.
Okay. Thank you.
Thank you for the paper.
Okay.